Okay, for part 2, we're going to continue on and look at transverse and longitudinal waves, interference, and standing waves. So, longitudinal transverse are just ways to describe the waves and how they move. And the idea is that when you've got the material, some waves, as they're moving, they just have the material going up and down. So that's a transverse wave. And we were talking about a water wave earlier. That is considered a transverse wave. So, like, here's a hand shaking a string. And the idea is that the velocity of the wave is actually away from the hand, but the little bits of string, they don't move side to side. They just move in an up and down motion as the wave passes by. So the wave energy is moving to the right, but the motion of the particles is up and down. And so that's called transverse, which is another word for perpendicular. Okay, so the wave motion is perpendicular to the displacement of the particles. And so here's a teacher with a bunch of sticks, and as she starts to wave these sticks that are tied down, the wave motion is traveling, but the sticks are just going up and down. So they just are tilting up, tilting down. They don't get to go side to side. So that's a definition of transverse. Now, for longitudinal wave, it's something more like a spring that you push and pull on. And in that case, the wave motion is still to the right. That's the velocity. So the wave travels from the hand towards the wall. But the particles along the way also move left and right. So they are compressed. So they move into a position where they're compressing. And then in other places, they are moved away. And that's called a rarefied area. And so they're moving away from one area, and then they'll reverse, and the compression is what passes through. So this area will become compressed, and this area will stretch out. So the particles themselves will be moving back and forth, but not very far. They don't travel to the wall themselves, right? The spring does not end up, all the coils don't end up at the wall, but the coils do move back and forth. And so the longitudinal wave you can think of as the parallel, because the displacement or movement of the particles is parallel to the wave motion. Whereas in a transverse wave, again, you can think of that as perpendicular. Now we're going to talk more about sound waves later. They are a type of longitudinal wave, and it's compression of the air molecules that occurs as the wave passes across a room. So I am speaking to you with air molecules that are being compressed as they head towards the microphone. And then when they hit the microphone, they cause it to a compression that is turned into an electrical signal. Okay, some other waves that are longitudinal waves and transverse waves are earthquake waves. Earthquake waves, actually, they're like 5 different types. But the main 2 types are the longitudinal and the transverse. And the longitudinal, on the first one, the P wave, is called, P is primary. It's the first wave that hits. And S is actually for secondary. It's the second wave that hits. And so the secondary one's a little slower than the primary one. And what happens is the primary is longitudinal, and it can travel through liquids or solids, or even through gases, because it can compress ahead of itself. Change colors here. So the wave is able to compress the liquid as it moves through it. So water waves are also underwater, are compression type waves. So, you can hear when you put your head down under the water in the pool or something, you can hear the sounds of the other people. So sound waves can travel through water. And that works by compression. But one of the things is that people learned a lot about the Earth and the fact that the Earth has a liquid outer core. So this orange ring here is the liquid outer core of the Earth. And the way that they figured that out was that secondary waves couldn't travel through it. Secondary waves would all stop when they reach this place, because when a secondary wave travels through, it tries to push material to the side, which in water will work. The water will go to the side, but it won't return. And so it doesn't oscillate. So the wave dies out very quickly because it can't, because the material it pushes doesn't come back. It has to have what's called a restoring force, which these water waves are not going to have, or liquid waves internally. Okay, so on the surface there's a restoring force. It's called gravity, and the fact that water molecules cling to each other. So water waves on top of water are can be transverse waves, but within the water, sound waves and stuff, those are going to be compression type waves, longitudinal waves. So transverse waves only work when they go through solids, because they need a restoring force. They need the molecules clinging to each other. But they can work on the surface of water. Okay, so that's for that. All right, now what's interference? Interference is the idea that when waves cross over each other, they can add or subtract. And this is called the superposition principle, which I always love that word. And what it means is super means above, and you're positioning them above each other, and they can add up. So here we see two waves where their peaks and their troughs are lined up. And that is what we call in phase. And so what happens is that their peaks add up. So if you measure this little bit and this little bit and add them together, they would reinforce to make a taller wave. And their trough would be a deeper trough. Whereas destructive interference is where the waves cancel. And so that can happen when you have waves that are called out of phase, where their peaks and their troughs are opposite each other. And so in that case, you've got a positive and a negative. They add together to make basically zero. Okay, cancellation of a wave. So this can happen in water. This can happen on a string or a spring. And so in water, you can see ripples. And if you go down to the river and you look down at the bridge supports that are supporting you or something, you'll see ripples in the water. And you can see where they're higher, where they cross over each other, where waves cross over. It can work with light waves. These are some laser beams over here on the left. Here's some ripples in nature. You can see how the waves interfere and add. Here's showing on a South Pacific island all these waves, and they cross each other. And so anyway, so we'll talk more about interference later when we need it. Okay, so we need it sort of for standing waves. The idea is, what if you send a wave out on a rope and then you send a second wave after it? And the one that hits the wall here will reverse and come back. Meanwhile, you've got the other wave coming also. And if you do this at just the right speed of sending waves, the right period or frequency, then what can happen is you can get what's called a standing wave, where the wave you send out and the wave coming back are perfectly aligned to cancel in some areas. Oops. So at some points, they're going to cancel. So like this point here and here will cancel always, as long as you keep that steady pace. And also we count this point as a cancellation and this point is a cancellation because where the wave hits and reverses on itself, it cancels itself at that point. And so anyway, so you send waves out and keep sending them out, and they keep canceling at those certain points. And so it's called a standing wave because it has a certain shape where some places are canceled and other places the wave would go like that. So let me do that for you. Okay, so you get the idea of what I'm saying. Let's see if I can pin this. Okay, hopefully that's pinning it for you. And so what I'm going to do is make some standing waves here. And I've got this tied, so hopefully it'll work. Okay, so the first standing wave, let's just start one. Here we go. And you can see how there's some places where it stays kind of still, right? And other places where it's waving up and down violently. Okay, now I have to make my hand move at the right speed. Now, if I make it go a little faster, I can get standing waves. But now these are shorter. And if I do it more slowly, I might just get a standing wave with one central, what is called node, in the middle there. Okay, so anyway, so yes, so as the wave was put out and it reflected and then it came back and you got yourself some standing waves. Now, there are certain patterns here. Now, nodes are the regions where you have minimal displacement. So that's where it canceled out and those stayed constant. And like I said, you count each end also, because my hand, where my wrist was basically a stable standing wave. Let's move back to the picture. Okay, so you get 4 nodes in this case. Antinodes is where it was changing its amplitude a lot. So antinodes, this one has 3 antinodes and 4 nodes. Vibrating, okay, so sometimes it cancels, sometimes it doesn't. So it adds positively, sometimes it adds negatively, and so you get all sorts of energy going on there. But you always cancel at certain spots if you can maintain it. So there's this picture in the book that might help you understand. It doesn't really help me very much, but the idea is a wave goes out, then there's a reflected wave. In some places they cancel and are out of phase. So you end up with a standing wave. Okay, so the standing waves have definite patterns. And so the fundamental, which we already talked about, is just like a jump rope, just up and down, up and down. And so in that case, it has one big antinode and 2 nodes, one on each end. In the second harmonic, okay, because that one's also called the first harmonic, the second harmonic has 2 antinodes. And then it will have 3 nodes. Now it has one in the middle. Notice the wavelength got shorter, right? The wave is shorter now. And so the third harmonic has 3 antinodes. Notice the pattern there. The harmonic number goes along with the number of antinodes. Whereas the nodes, if you have both ends tied or held, as opposed to loose, flopping like a whip, the end of the whip would flop around, then you will always get another node on the end. So you always have an extra node. So that's why we have 4 nodes here. There's some other things too, though. There's a relationship then between the length of the string and the wavelength. And there's also a relationship between the harmonics and their frequencies. So the fundamental mode, that frequency gets multiplied. As you go to the second, it's multiplied by 2. So if you have 200 hertz for the fundamental F1, frequency 1, the second harmonic would be 2 times as much. So F2 would be 400 hertz. And the third harmonic would be F3, 3 times 200. So that gives you 600 hertz. Okay, so the frequency is actually a multiple. The nth frequency, so for the nth node, I said nth harmonic, so n being the counting number, is going to be n times the fundamental frequency. And that equation is not in your equation sheet, so you might want to write it down. It comes in useful sometimes. It's also needed for your lab. Anyway, so the nth frequency is n. So like for F2, the n is 2. For F3, the n is 3. Okay, times the fundamental. All right, so let's look at the length. Well, one thing is that, remember we talked about how for guitar string, up and down, fundamental motion, that's just half a wavelength. So the length of the string is half a wavelength. Now, you can see for the second harmonic, I have a full wave, an up and a down. So in that case, the length is equal to a whole wavelength. And when I go to the third harmonic, well, I've got a full wave plus an extra half wave. So the length is actually 3 halves of a wavelength. In fact, the distance between two nodes is always going to be half a wavelength. Okay, and the distance between a node and an antinode is going to be a quarter of a wavelength. Anyway, so yeah, so I've got 3 half wavelengths down below. Now, there are more harmonics. There's the 4th, the 5th, the 6th, the 7th, the 8th, the 9th, the 10th, the 11th. It doesn't stop necessarily, except as they don't have any energy, so they don't become relevant, or the frequency becomes too high to hear. But in musical instruments, which we'll talk about in chapter 21, those harmonics are what gives sound its richness. Okay, so a guitar plays a note of 196 hertz. That's a G string on the guitar. And it's in the third harmonic. The guitar string is 60 centimeters long. What is the wavelength? What is the wave speed on the string? So when we're in the third harmonic, we've got this relationship. The length is 3 halves of the wavelength. So we'll need that. So when we want to find out what the wavelength is, we need to reverse that to wavelength and multiply both sides by 2/3. So it's going to be wavelength is 2/3 of the length. Okay, so we've got the length here at 60 centimeters. And 2/3 of that is going to be 60 divided by 3 is 20. 2 times 20 is 40 centimeters, which is 0.4 meters. Okay, so we've got the length. Now we can go ahead and finish up what's the speed of the wave on the string. So we've got a frequency, right? Because we're going to use that equation again. Velocity is wavelength times frequency, or frequency times wavelength, either way. We've got our wavelength, 0.4 meters. We're going to multiply by our frequency of 196 hertz. And we're going to end up with, well, whatever 0.4 times 196 is. That's 78.4. And what's that going to come out in? Well, it should come out in meters per second, right? We're looking for velocity. But let's look at the units here. We've got meters, and then we've got hertz. Now, what are hertz? Hertz, of course, are cycles per second. Okay, so you can see where the meters per second comes from, but what happens to the cycle? Well, cycle kind of appears and disappears, kind of like the Cheshire Cat in Alice in Wonderland. Because the thing is, it's implied for wavelength. It's 0.4 meters per cycle, right? Because we're saying it's one wavelength. So the thing is that really we can cancel out those two cycles, but they're kind of just implied. So anyway, so don't worry about the cycle unit if you probably weren't worrying anyway. But it should come out properly to meters per second here. Okay, and that's the end of that. We're going to go on to part 3 next. So for part 3, we're going to be looking at the Doppler effect, bow waves, shock waves, and the sonic boom. Okay.